All right, ladies and gentlemen, thank you for flying here about this beautiful day. Let's take a gander here. And before we jump into the actual content, please look at what our goal for today is. We're going to review ideas of reflection like you did in geometry, maybe in Algebra 2, rotational symmetry. We're going to apply them to graphs, and something called even and odd functions. That's going to be superific. All right, so first thing. How many symmetry lines does a square have? All right, so notice we've got a vertical line, we've got a horizontal line, and on top of that, we can go diagonal here, and lastly, diagonal here. So we've got 4 lines of symmetry in this square. All right, what about the centers of symmetry there? What about the centers of symmetry? How many centers of symmetry does this have? Where?
Right in the center.
Good. Hashtag right in the center. All right, and the reason for it is this. So when we flip this thing, that's ugly. When we flip this thing around, so if I were to just rotate that, like that, notice that it maps onto itself, like so. And officially, when we're talking about symmetry, rotation, we should rotate 180 degrees, like so. So I went 180 degrees around. In other words, this point here maps to this point there, and this point here maps to that point there, etc. Okay? So, and that would be correct. That would be 1 there. So the answer here is 4. This one here is 1. How many symmetry lines does an isosceles trapezoid have? This guy is not symmetrical here because this point maps to here, which is in the trapezoid, not on the trapezoid. So we can't say it that one, but we could say this because this point maps to there, and this point pre-image maps to this image if we were talking like transformations that we did earlier. Can we do lines to the corners? I mean, I can draw a line to the corner, sure, but notice what would happen. This guy here, right there, would map to right there, which is no longer on the trapezoid. All right, so that answer there is just 1 as well. All right, how many centers of symmetry does this have? And the answer is 0, because no matter what, if I map this here and I try to rotate this guy, notice what will happen here is that as I rotate it, it doesn't map to itself. Notice that it's now funky-dunky. All right, so that one doesn't work. So, la respuesta, 0. So now draw a figure with more than one center of symmetry. So if we start thinking about things like a stop sign or others, notice that the the center of symmetry remains the same. But doesn't it rotate just a few degrees that way to get to itself? Yes, but the point is the same. So this one would not work so well, but notice what does work. Just a line. What do I mean? I could rotate it right there. Because it goes on forever, it would map to itself. If I rotated it here, it would map to itself, and the same thing here. Some of you may or may not know something called the sine curve.
I am a man. Oh, I am a finite world.
Sure.
So it says 0, 0, and there's no loopy curve.
So notice this one here, too, is any of these points along, I could rotate it here, I could rotate it here, I could rotate it here. The sine curve or cosine curve also would be have multiple points, centers of symmetry. All right, so we're going to review a little bit, hopefully most of this review, and if it's not, that's okay. We're going to catch you up for those of us who have long or very short-term memories. The first thing we're going to talk about is what's called reflection-symmetric. Notice the adjective there. A figure is reflection-symmetric if and only if, anyone remember in geometry, if and only if? Yeah. That means it goes both directions. It's kind of like a definition, but all right. If the figure can be mapped onto itself by a reflection over
The rainbow.
a line. And for now, we'll just call it line B, but it can be any line name, any line. And this line is called the axis or line of symmetry. The axis or line of symmetry. It can be a vertical line, horizontal line, anything at all. So as we see, for example, if I have a basic shape or a function, in this case, just like a quadratic, we can see here that this line right here acts as a line of symmetry, or the axis of symmetry, because this point will map over to this point there, and this point here will map over to that point there. Or if I were to fold this function in half, fold it using this way, then these would lay on top. All right, so that's called reflection-symmetric, or the lines of symmetry based on reflection. The next is called point-symmetric, and this has to do with rotation, not reflection. And a figure is point-symmetric if and only if the figure can be mapped onto itself under a rotation of 180 degrees around some point. And generally we just call that point P, but it could be anything. So like we saw earlier with the square, I can rotate about the point right there, and I can rotate around 180 degrees, boop, and then it maps back to itself. There we go. All right. So here's your goal right now. Here's the original diagram that you have. You just have this dog leg sort of thing, clunk, like that. And you are going to draw the other half of the graph. So this is half the graph. And so you're going to draw the other half so it is point symmetric about the origin. Next, you're going to draw the other half so that it's symmetric with respect to the y-axis. In other words, here's the y-axis. You can reflect it on that. Next, if it were reflected this way, and then, of course, you're going to see about all of them combined, how would you describe them? So take a few minutes right now with your or without your partner. Go. So now that you've done this, let's take a gander here. And notice this point is going to map down to this point right here. So it comes along this. And then notice the slope here kind of looks like it goes down one, right one, 2, 3, 4-ish. So I'm going to go up one, right 1, 2, 3, 4-ish. So plot to here and connect the dots. Okay, so this is my A right here. And now let's repeat the process for the other scenarios. So the next one here says, draw the other half of the original graph so that the result is symmetric with respect to the y-axis. Here's the y-axis. So that means the red point maps to here, and the end result maps to there. So essentially all I need to do is connect the dots, like so, label B. And lastly, let's check on the last one here. We're going to draw the other half of the original graph so that the result is symmetric with respect to the x-axis. We're going to label this. So that means if it's along the x-axis, it's going to reflect in the x-axis. So that point reflects to there, and this point here reflects to here. So I just connect the dots like so. Okay, now I'm going to erase a little bit before we move on there. So now we're in a position to answer the last question. What symmetries of the complete diagram, that is the union of the origin, so this whole Spider-Man looking thing, does this possess? So what are all the symmetries? Well, let's see here. Notice it can reflect this way because this point reflects there, this reflects there, this reflects there, and this reflects there. Good. So we have reflection over the x-axis. What else does it have? It also reflects along the y-axis. As we can see here, this point reflects across, like so. And notice that if I were to rotate it here, about this point, the whole thing can rotate. Well, that one doesn't work so much. But then the whole thing can rotate nicely. So it also has rotation symmetry about the origin, or about 0, 0. All right, so let's take a gander at our lovely little theorems about reflections and rotations. And without a graph, how we can do this magic style. So the graph is symmetric with respect to the the y-axis. So it is a vertical line of symmetry. So we would call it a horizontal reflection because it reflects horizontally. In that case, it's if and only if for every point xy on the graph, then what else is true? That negative xy is also on the graph. So how do you summarize that? Opposite of x. So let's unpack this one. A graph is symmetric with respect to the x-axis if and only if for every point xy on the graph, x to the negative y is also on the graph. So that one, if we want to reflect something across the x-axis, we just take the opposite of y. Notice what we're taking the opposite of. If I want to reflect it on the y, I opposite the x. If I want to reflect it on the x, I take opposite of y. Which leads us to the last one here. A graph is symmetric to the origin. In other words, it rotates 180 degrees like so. If and only if for every point xy that's on the graph, so is the opposite of both of them is also on the graph. By the way, we're not saying here that we start in quadrant 1 and we go to quadrant 3. All we're saying is that when both of these flip, they change places and they're still in the same, it looks exactly the same. And you could have something that starts here in quadrant 2, or like it's going through both of those quadrants, and when you rotate it, it'll still be in both of those quadrants. All right, so what's the key on this one? Is you take the opposite of x and y, like so. And that'll give you rotational symmetry. Okay, so we're going to look at this two things. Number one, we're just going to see what happens, how we can demonstrate that with a single point. If we're going to see that it reflects over the y-axis, and then we want to prove it for every point x, So this proof here is an actual proof. Takes 13 seconds, no big deal. This one here is just a check. So notice what happens. When I put in a 2, out comes 2/10. So now what we're saying is, according to reflecting over the y-axis, if we're going to reflect over the y-axis, that's this one here, reflecting over the y-axis means that I should be able to put in the opposite of x and get the same y. I get the opposite of x, and I'm going to get the same y. So in this case, I'm going to say, well, what is f of negative 2? When I evaluate this at f of negative 2, I should get, my expectation is the output is the same. The output should be the same. So let's just plug and play, see what we get. Notice the double negative there becomes positive, so that's 1 over 4 plus 1, and that's 1/5. And for those of you who know your conversions, there we go. So I've demonstrated for this example. If I plug a 2 in, I get 0.2. If I plug a negative 2 in, I get 0.2. So that works for one point, but does it work for every point? So how do we test it for every point? Well, if x is in, what's the other one that's also in? Negative x. So let's now substitute in negative x. So remember, when we substitute in, all you do is substitute in the negative x there in its stead. But of course, mathematically, negative squared is positive. So we end up with x squared plus 1. So notice f of negative x is the same as f of x. So if I put the opposite in, I still get the same output, no matter what. If I put x in or negative x in, I'll get the same output. Our next thing is that we can use symmetry to help in graphing. As you know, that if something is symmetrical, we can easily just graph the other half just by essentially copying points over. Okay? So let's look at example number 3. Symmetry can help when graphing a relation or a function. Remember that a relation could be rotated so it looks like this instead. So that's why it's differentiated there. So for example, no capital letter there. Draw the other half of the graph of y equals x squared minus 4 after testing for reflection symmetry over the y-axis. So first I'm going to test it. How do I know it works? Well, let's see this. Y equals, let me plug a negative x in right there. And if I get the same function coming out, then I know I can just trace it over. So negative squared is positive. So since I ended with where I started, I now know all I have to do is start taking points like this one and moving it over to there. This one here, and I think I went too far on that one. So this one is right there in the middle on the third one. So that one's right there. This one here is on the axis. This one is halfway in between about on that first one. So something like that. I'm just grabbing a bunch of points and pulling them over. And then to the best of my ability, I'm going to fit the curve nicely like so. In example number 4, we're going to test to see if the equation xy equals 12 is symmetric with respect to the x-axis, the y-axis, or the origin. Then we want to complete the graph. So there's a good chance this thing could be graphed like this, or it could be rotated all the way over there, or it could be reflected this way. I don't know which quadrant to draw its partner curve, or even if I should, so I have to test it first. So you're going to test it first by substituting in a negative y to see if you get the same. Try negative x, and then try them both. So for each one of these, I have to substitute in accordingly. So this one, if I plug in a negative x back to my original function, which is xy equals 12, notice that I get negative xy equals 12. Is that the same? No, it's not, because it's not xy equals 12. It's not the same. All right, so let's try the substitution differently. So x stays the same this time. Negative y changes. And now let's see what we get. Hashtag, it didn't work. I got the same as this one, but it's not the same as the original. Oh, so now let's test on the origin, where I'm going to plug in new or opposite values for both of them. Here. Now, double negative is positive. Dun, 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 dun. This one is lo mismo. Yes. Ka-chow. So now we know it reflects on the origin, which means that this function right here is going to rotate around something like, whoa, let's see if we can do it. Whoa, it's going to rotate around to like there. Okay? So I'm going to redraw that to be something like this. And it roughly crosses there, so I'll make it cross here. Roughly crosses there, so I'll make it cross here, and then just estimate the rest. And it does asymptote closer to the axes, as we can see.
I guess it's
All right, so on this next part, I asked you to compare and contrast the following functions, which includes sort, group, and label. That is, if you were to put these in groups of like something or another, what would you do it? How would you do it? And then what would you call them, or why would you call them that? So I'm looking for some insight here. So for the even ones, that is the even exponents there, we have a basic U shape or quadrant 1, quadrant 2. Good. And so as we note here, this one goes through not adjacent quadrants, but rather, I guess, opposite or vertical quadrants there. So this would be an odd number, and this would be an odd number or an odd exponent. And in that case, it has a slightly different behavior than that. Okay. What else do we notice? What type of symmetries do each one of these have? When the exponent is odd, we have point-symmetric. In other words, rotational symmetry. And same thing here, point-symmetric over there. So this one, the even one there, is not point-symmetric, but what do we call it? Reflection-symmetric? Reflective, reflection-symmetric. All right, as is that one. And if you were to zoom in, we can see quickly here that it's on the axis, but not necessarily have to be the axis every time. It just reflects across that particular axis there. So here's where definitions come into play on the next page. Using that information, for the power functions, f of x equals x to some power, x to the n, where n can't be 0. When n is even, we notice that the graph is reflection-symmetric. So, using the converse of that idea, in other words, if a graph is reflection-symmetric, then it must be even. Now, of course, you learned in geometry back in the day that the converse is not necessarily true. Yes, that's true, but for the sake of definition here, they've taken the converse and applied it in this case. So, an even function. An even function is an even function if and only if, for all values of x in its domain, f of negative x will yield you f of x. In other words, symmetric in relation to the y-axis. So this follows. For the power functions, f of x equals x to the n power when n is not 0, and n is odd, the graph is point-symmetric. In other words, we can rotate. It has rotational symmetry. Thus, the converse has been used as a definition of an odd function. A function f is an odd function if and only if for all values of x in its domain f of negative x is equal to, but watch the magic here. If you take the opposite of x, that means you're taking the opposite of your output. That is the opposite of f of x. So in the first case, it's kind of like taking the absolute value of the x. Down here, it's like taking the opposite of the output. Opposite of the input gives you the opposite of the output. So, determine whether the function f of x equals 4x minus 2x cubed is even, odd, or neither. If it appears to be odd or even, prove it. So, how do we determine it? Well, so far, what we've seen is by graph. Okay? Now, of course, your instinct might say, oh, look, Swenson, that looks like a 3, so maybe I'm thinking it's odd. But let's go ahead and pull out a handy-dandy graphing calculator and graph this puppy. Zoom in, zoom out, etc. So when I plug this into a calculator, notice what I think. Notice that it goes here, down, and up. So it looks, if I were just to rotate things, it looks like it just rotates on itself. Notice that I don't think it's probably reflection symmetry. Notice because this one here does not map over to here. Oh, it does map from here to here, that's true, but that's the only point that actually does it. Or this one maps to itself. But this one might actually map over to there, but this one clearly doesn't map over to there. So I can say that some of it behaves kind of like reflexive, but in the end, I would say rotational probably. So I think it's rotational, therefore I think it's probably odd. So to test the odd, I have to input the negative x, and what I expect to get is the opposite of this one. When I put in a negative x, I expect to get the opposite of the output. So now we have to test that. So f of negative x is equal to 4 times negative x minus 2 times negative x cubed. Okay, so now when I finish this up, watch the magic, watch the magic. Negative 4x, because I can just use the commutative property and associative property there. Now notice here what happens. Negative times negative times negative is negative, so that becomes oppositified, right? So now I get this. Now what's the magic? If I factor out a negative from this term and from this term, that means I oppositify this one. So now I write down a positive 4x. And I oppositify this one, so I bring down a negative 2x cubed. And let's see how that compares to the original. Oh, look, the opposite of the original. Here's my original, there's the opposite. So putting in a negative yields me the opposite output. Opposite input yields me opposite output. Therefore, this puppy is odd. The last thing what we're going to do on here is that we're going to graph with symmetries. So graph with symmetries do not need to be symmetric over the x or the y-axis, so they can reflect anywhere else. So what we're going to try to figure out is in this function, what are the lines of symmetry on this situation? So because we know that the parent function is 1 over x squared, we know what it should look like. 1 over x squared. It's basically going to look like this here. So I'm just going to try to figure out, well, where is the vertical asymptote and where is the horizontal asymptote, or where is the reflection, the line of reflection there. All right, so what to do is I see how it shifts. So because this is a plus 3, I can see that this is going to shift to the left 3. And then this part it's going to shift down 7. So instead of originally being asymptoted here, it's now going to shift down, shift left 3 and right 7. Excuse me, and down 7. In shifting left 3, I am going to have my vertical asymptote or line of symmetry there. And next, since I'm going down 7, this right here, asymptote, is going to go down 7 as well. So 2, 4, 6, and 7. So it's kind of like me just taking my axes, x and y axes, and shifting this way. And now, since there is no stretch, which happens in front like this, it's effectively just going to be the exact same here. Like we did, all we do is shift, just take the axes, relocate them down here, and then I have my new function, or the sketch of my graph there. All right, that concludes our time. Please spend some time summarizing down below and work on your assignment.